Hey guys, so today I'm going to be walking you through Chapter 3 material, which is about numerically summarizing data for your Math 200 class. So we're going to, just like last time, we're going to be toggling between StatCrunch and PowerPoint. So I'm going to kind of keep this minimized here so I can toggle between the two. I have a bunch of data already in here that we're going to use. I'll show you how to do some of the calculations that are kind of easier by hand, but we're going to be relying on the technology to do a lot of this stuff for us. So section 3.1 is all about the measures of central tendency. And the first thing that we start out with is the mean, which I'm sure you have all heard of before. It's also known as the average, okay? So we can either have a population mean or a sample mean. So the population mean is denoted with this symbol right here, which is the Greek letter mu, okay? And we would have a population mean if we used all individuals in a population. And if you recall from chapter 1, that would mean that this is actually a parameter because it's from a population. Now we also have a sample mean, and typically that's written as x bar. It's not showing up here for some reason, but it's just a little x with a bar on top of it. That's going to be the symbol that you're going to see for that. And that's computed using some kind of sample data. So where we don't have access to the full population, we might take a sample. Now, since we're talking about a sample, that means that we have a statistic, again, from chapter 1. So again, to kind of summarize this, population mean, we use the letter mu, and that's when we have all individuals in the population. And sample mean, we use x bar, and that's when we just have a sample of our data. Now, in order to actually calculate the mean, you should all kind of have an idea of how to do this already. Really what we do is we add up all our observations and then we divide by the number of observations that we have. So for example here we have travel times for 7 employees of a startup web development company. So these are all their travel times. We have all 7 of them. This is a population because we're just interested in the startup web development company. So we're only interested in these 7 individuals. So we have all of this data. If we wanted to calculate the mean by hand, it would be really easy. We would just add these up and then we would divide by 7 since that's how many observations we have. But we can also just do this using StatCrunch. So if I hop over to StatCrunch here, I'm going to go to Stats, Summary Stats, Columns, okay? So let me just get my stuff gathered here. So I have travel times, that's this column right here. So I'm going to do Stat, Summary Stats, and then Columns. And I'm going to select travel times because that's the one that I'm interested in. And then all I really want is just the mean, so I'm just going to select that. Now if you notice, there was a bunch of stuff that was highlighted over here. Okay, I really only care about the mean for right now, so I'm just going to highlight that. I press compute and kind of displayed off the screen here, but it gives me a mean travel time of 24.857, and right here you can see that that would round to 24.9, which is what I have here. Now, since we're talking about everything in minutes, our mean is also in minutes. And you'll notice that the Greek letter mu is used here because of the fact that we're finding a population mean since we have data on all 7 of our startup web development company employees. Now, the next thing, oops, sorry, this is displaying funny. Okay, the next thing we want to talk about is the median, okay? And you've probably also heard of this before. The median just describes where the middle of your data is. Now, I'm going to walk you through the steps for finding the median, and then I'm also going to show you how to do it using StatCrunch. Again, it's pretty simple. So if you're going to do this by hand, what you first need to do is you need to arrange your data in order, from smallest to largest or largest to smallest, either way. And then you need to figure out how many observations you have and find the middle observation. Now, if you have an odd number of observations, then the median is just going to be exactly in the middle of your data set. And if you want to find where the middle is, all you need to do is you need to take the number of observations you have, you need to add 1, and then divide that by 2. And that's going to be the position in which your middle data point lives. Now, if we're dealing with a small number of data items, it's not going to be very hard to see where the middle data item is. But this is a nice formula for if you have lots and lots of observations. Now, if you have an even number of observations, then what you do is you find the 2 middle observations and then you take the mean of those. So really what you're doing is you're taking the observation that lies in the n divided by 2 position, so the number of observations divided by 2, and the n divided by 2 plus 1 position. And then you take those, add them together, and divide by 2 to find the mean of those numbers. So if we look back at our observations here that we have for our 7 startup employees, you can see here we've just arranged them from smallest to largest, 5 all the way up to 43. And if you notice, we have 7 observations, which is an odd number. So all we need to do is we need to add 1 to the number of observations and divide by 2. So we get 4. So we know that our middle observation is going to be in the 4th spot here. So our median is going to be 23. And since we only have 7 observations, step 3 is kind of silly to do, because what we can just do is we can look at our observations here and we can kind of cross off. I would cross off the lowest number and then the highest number, the next lowest, the next highest, next lowest, next highest, and I would be left with a 23 in the middle. So it's pretty easy to visualize there. Now, you can just use StatCrunch to do this as well. So I have the same data. I'm going to go back here. I'm going to go to Stat, Summary Stats, and Columns. I want the travel times. And really all I care about this time is median, so I'm just going to select that, press compute, and it gives me a median of 23, which is the same answer that we got when we did this by hand. Okay. Now you can get the mean and the median at the same time by selecting them both, and I'll show you guys how to do something like that in a minute. But I'm just showing all of these things kind of one at a time for right now. All right, let's say that now an additional new employee has been hired, okay, and their travel time is 70 minutes, and I want the median of that new data set. So if you look here, you can see the 70 is kind of tacked on the end here, so now I have 8 observations, which is an even number of observations. So if we take a look at our middle 2 observations, you'll notice that we have, let's see, it looks like 23 and 26 are both in the middle here. So if you look at 23 and 26, those 2 numbers are your middle 2 numbers. And then what you do is you just take those, add them together, and divide by 2. Since we had 2 numbers in the middle, we just take the average of those 2 numbers. So we end up with a 24.5 for that median. But again, StatCrunch comes to the rescue. It's really easy to do it in here. So I have an adjusted travel times column where I added the 70. So I'm just going to go to Stat, Summary Stats, Columns. I'm going to select my adjusted travel times because that's the one that has the 70 on it. And again, I just want the median. And it gives me a median of 24.5, which is the same thing that we got doing it by hand. So either way works. When you have a small number of observations, you can kind of almost see what's in the middle, particularly if they're already ordered, so it might be faster than opening up StatCrunch. But if you have a lot of observations, you definitely want to make sure you're using the technology to help you. Now, we say that a numerical summary of data is resistant if extreme values, meaning like really large or really small relative to the data that you're talking about, don't actually affect the value substantially, okay? And we'll talk about what this means in practice in a little bit more detail in a few slides. But right now I want to just talk about skew. So we talked about skew back in chapter 2, but I want to kind of show you how it works when we're comparing the mean and the median and how those differ based on the skew. So if we take a look at this observation or this distribution that we have right here, we have a distribution that's skewed left because it has a tail on the left. And if you take a look at it, the mean actually lives kind of in the tail, and then the median is more towards the middle of the data, okay? So in this case, your mean is actually smaller than your median. So when you have something where the mean and the median differ by quite a lot, and the mean is smaller than the median, that would indicate that you have a distribution that might be skewed to the left. And if you look here, this table is saying the exact same information. Skewed left indicates that we have something where the mean is substantially smaller than the median. Now, if you have a distribution that's symmetric, the mean and the median actually both kind of lie smack dab in the middle of your distribution here. Now, it says mean roughly equal to median because rarely are your mean and your median going to be exactly the same, even if you have a symmetric distribution. We can always kind of account for a little bit of variation that's going to exist between those two. But if they're roughly equal, then you could say that your distribution is symmetric. Now, if you have a distribution that's skewed right, meaning you have your tail on the right-hand side, again, if you look here, the mean is kind of hanging out in the tail over here, just like the mean was in the tail over here. but in this case the mean is larger than the median because again the median is closer to this high point in your data. And your median in this case is to the right of it, okay? So mean is substantially larger than the median when you're talking about a distribution that's skewed right. So what we're going to do next is we're going to look at this data where we have asking prices of different homes for Lincoln, Nebraska. So I have all of the asking prices here, okay? Let me close out of this. Home sale prices. So what I'm going to do is I'm going to take these home sale prices and I'm going to calculate some summary statistics. So I'm going to select home sale price from my column, and I'm going to come down here, and I want the mean and I want the median as well. So what you can actually do is you can hold down on the, let's see, I have a Mac and it's the command key. I'm not sure which Windows key it is, but you're just going to select both the mean and the median at the same time. If you use shift, it's going to highlight everything that's in between. That's okay, it's just a little more than what we actually want. But I think it'll be the control key or something like that on a Windows keyboard. But you're just going to select mean and median, and I'm going to click compute here, okay? And you'll see that it gave me the mean and the median for my home sale price. And let me just move down a slide. So the mean asking price is $168,320, which is what we found right here, and we just rounded to the nearest whole dollar. And the median is $148,700. Okay, so if you take a look at these, if we compare the two values, and again, this is how we got these values in StatCrunch. We went to stats, summary stats, columns, and then we selected the median and the mean at the same time. But if you take a look, the mean is larger than the median, and what you want to keep in mind is that the mean is going to live in the tail of my data, okay? So that means that my tail is going to be on the right since the mean is larger. So what we would actually decide is that the distribution is most likely skewed right. Now, another thing we can do is we can draw a histogram of this data. So we did this back in chapter 2, but just a little refresher is always a good idea. So let's recreate our histogram that we have here. So we'll try to do it kind of the same way that they have here. Let me scoot these over for a second so we can see what our bin width is. So let me close out of this, and we're going to do graph and then histogram, and I'm going to select my home sale price there. And it looks like I want, let's see, I want the width of my bars to be 25,000. And then I probably want to start my bins right around 50,000 just so I have a little gap there. And I just want a frequency distribution. I don't need relative frequency or anything like that. And I'm just going to do compute here. And we should get something that looks pretty similar to the graph that we have here. And if you take a look at that, these should look just about the same. It's just different colors, okay? And if we take a look at this histogram, or the histogram we created, same thing, what you'll kind of see is we have something where we have, if we kind of overlay a curve on here, we're going to have something that is in fact skewed right, just like we decided one slide back when we said that the mean was larger than the median, which would also lead to the same conclusion. So this is just a way of kind of verifying that the distribution is skewed in the way that we think that it is. Now, mode is a third sort of measure of central tendency that we sometimes see. It's not used as often as median and mean, but it is very useful when we're talking about categorical data. So for example, if we were talking about, let's say, favorite sports or something like that, we would be able to talk about the mode there, but we wouldn't necessarily be able to talk about a mean or a median since we have categories and not numbers, okay? So the mode is just the most frequent observation that occurs in a data set. A set of data could have no mode at all if there are no repeating observations. It could have one mode, or it could have more than one mode. And if no observation occurs more than once, we just say that the data has no mode. If we take a look here, this is a frequency table, and it just gives state, and I don't remember what these tallies are for, but that's okay. You can still see the data. Massachusetts has a frequency of 3. I'm not sure what we're talking about here because I forgot the context of the question, so I apologize for that. But if you take a look at our highest frequency, it's going to be New York with 8. So that would mean that the mode is New York. okay? And again, this is useful because we're talking about categorical data, meaning states, and we wouldn't be able to find the mean or the median if we're talking about states because it doesn't make sense to talk about an average of states. So one kind of nice measure of central tendency that we can talk about in this case is in fact the mode. Now, if you're given a frequency table, the mode you'll just be able to see by picking the most frequent observation, which in this case is New York. We can also find mode very easily. If I just go back here real quick, let's just find mode of that sale price. So if you want to find mode, you just go to summary stats columns. We do this the exact same way that we found mean and median, but instead of selecting those, all you have to do is just go down here, and mode is somewhere on here. Mode is the very last thing. So I'm going to go ahead and select that and click compute, and there are no unique numbers, so there is no mode for the sale price data, but if there were one, it would give me that there. So again, stats, summary stats, and then you just select mode. So to kind of summarize the measures of central tendency, we have the three kind of main measures. We have the mean, which is found just by adding up all of our observations and dividing by the number of numbers. We distinguish between population and sample mean, depending on what kind of data we're talking about. And the interpretation can just kind of be thought of as it's sort of the center of gravity, okay? And when our data are quantitative and the frequency distribution is roughly symmetric, the mean is probably the best kind of measure of central tendency to report. Now, the median is found by arranging the data from smallest to largest and then finding the middle. And in order to interpret it, really what we can say is that the bottom half of the data and the top half of the data are separated by this value. And this is useful when we have quantitative data again, but when we have skewed data, it's kind of a nicer measure of central tendency to use than the mean. Now, mode, all we have to do is just tally our data and find the most frequent observation. Now, this is probably most useful when you have qualitative data, and it's kind of the only measure of central tendency that we can report. So let's move on to section 3.2, where we talk a little bit about measures of dispersion. Now, range is probably something you've heard of before. It's very easy to calculate. All you have to do to find the range is just take your largest data value and subtract your smallest data value. So if we go back to our lovely company data, okay, and we want to find the range of this, all we need to do is we take our 43, which was our longest commute time, and our 5, which was our smallest or shortest commute time, and then we just subtract those two, and we end up with 38 minutes for our range. If we want to do it in StatCrunch, we do this by just going to summary stats columns. This is the same place, the only place we've gone so far in StatCrunch for this chapter. And I'm going to select the travel times data. And then instead of all this stuff, really all I want is the range. So I'm going to select that, click compute, scoot this over, and it gives me a range of 38, just like I got here. Now, the next thing that we have is the population standard deviation, okay? And if you would like to see the formal kind of definition of this, you can check your textbook. But really, in order to find a population standard deviation, all we do is we take the square root of the sum of the squared deviations around the population mean, and then we divide that by the number of observations in the population, which is going to be large N. So that is to say that it's just the square root of the mean of the squared deviations about the population mean. Now, if you want to see this formula actually written out, go ahead and check your textbook. I did not put it here, okay, because we're going to be using technology to actually help us calculate the population mean. Now, population mean is typically symbolized by using the lowercase Greek letter sigma, which looks just like this right here. And then the variance is just the square of the standard deviation. And once you have the population standard deviation, you can just square it to get the variance. You can also use StatCrunch to calculate both of these things. So if we take a look at our data here, we have our 7 employees again. Okay, so we have all 7 of their travel times. This is going to be a population standard deviation because we're only interested in this particular startup web development company. So what we do in this case is we go to stats, summary stats columns, okay, and then we want the population standard deviation and the population variance. So what we actually do is we select what is abbreviated as unadjusted standard deviation and unadjusted variance. The adjusted standard deviation and adjusted variance have been adjusted for samples, okay? So if you have a population, you want to select the unadjusted versions, okay? So I'm just going to go back here to my travel times. I'm going to go to Stat, Summary Stats columns. I'm going to select my travel times, and all I want is that unadjusted variance and the unadjusted standard deviation, and they live right next to one another. So I'm just going to highlight them both, and I'm going to click compute, and you'll notice that it gives me these two values side by side. So my unadjusted standard deviation, that's my my sigma right here, that's 11.36 minutes. It's rounded from this value here. And then my unadjusted variance is the square of that. It's 128.98, okay? Now, if you actually take the value of 11.36 and you square it, you get something that's very close to this. You won't get exactly the same thing because the 11.36 was already rounded. Okay, so if you want exact values, make sure you actually have StatCrunch calculate the variance for you as well. Okay, now we also have something called a sample standard deviation, which is typically just denoted using the lowercase letter s, and it's just the square root of the sum of the squared deviations around the sample mean. And then instead of dividing by n, which is our entire population size, what we do is we divide by n minus 1, where n is the sample size. And again, if you want to look at the precise formula, it can be found in your textbook. Now, just kind of a little side note here, we're going to be talking about degrees of freedom quite a lot in this class, and n minus 1 is called the degrees of freedom. And if you kind of think your way through it, the first n-1 observations have freedom to be whatever value they wish. But that last observation, the nth value, has no freedom. It kind of is forced to being the sum of the squared deviations about the mean, or it's forced to be the value that makes the sum of the squared deviations around the mean equal to 0. And this sounds a little complicated, but I kind of want you to think about it like this. So if you imagine that I have exactly one piece of candy for everyone in the room, and I start maybe on the front right side of the room, and I ask the first person, which piece of candy do you want? They have freedom to pick any of the candy. Same thing with the second person. They have freedom to pick whatever candy they want. And that's the case all the way around, okay, to the n minus 1th person, okay? So the second to last person still has freedom because they're going to have two pieces of candy to pick between, but that last person is kind of stuck with whatever piece of candy is left, okay? They have no freedom. So the degrees of freedom is n minus 1 because up until that nth person, everyone has freedom to kind of choose, okay? But that last person is forced into kind of whatever makes, in this case, whatever piece of candy is left, but in the kind of statistics case, it forces the sum of the squared deviations around the mean to be equal to 0. And we'll talk about what that means a little bit more later in the course. So if we just take a sample of data, so let's take our 7 employees and we're just going to look at 3 of them. So we just have a sample. And let's say that we want the sample standard deviation for these 3 employees. What I'm going to do is I'm going to go to StatCrunch here, and you'll see I have entered those 3 employees here, the 5 minutes, the 26 minutes, and the 36-minute travel times. If I want the standard deviation and the variance for this, all I'm going to do is summary stats columns, okay, and I have sample travel time, so I'm going to select that column. And now, instead of selecting the unadjusted standard deviation and the unadjusted variance, I'm just going to select plain old standard deviation, plain old variance. So I'm going to go in here, I'm just going to select variance and standard deviation. I'm going to click compute, I'm going to scoot it over so we can see, and you'll notice that our variance is 250.33, which is exactly what we have here, and our sample standard deviation, that's denoted with an S, is just 15.82 minutes. So again, you would be able to calculate these by hand. It's a little bit tedious, so I would rely on StatCrunch to actually do this for you. Oops, sorry. Okay, So the next thing we're going to talk about is the empirical rule, okay? And this is something that we're going to do kind of without the help of technology, okay? So this is kind of one of those things that you probably need to know and understand. But what we say is that if a distribution is approximately bell-shaped, then about 68% of the observations in that data are going to lie within one standard deviation of the mean. Now, 95% of your observations are going to lie within two standard deviations of the mean, and 99.7% of the observations are going to lie within three standard deviations of the mean. So this is also referred to as the 68, 95, 99.7 rule because of the fact that these three values kind of dictate what percentage of the observations are within 1, 2, and 3 standard deviations. Now, it's important to note that you can also use the empirical rule based on sample data. We would have x bar in the place of mu, and we'd have s in the place of sigma. So if we take a look here, this is kind of a sort of visual depiction of the empirical rule. You're going to have your mean in your middle of your bell-shaped curve, okay? And then what we're going to do is you're going to take your mean and you're going to subtract a standard deviation, subtract another standard deviation, and subtract another standard deviation. And you're going to label all of those values as you go. And then you take that same mean and you're going to add. Okay, so you're going to add a standard deviation, add another standard deviation, add another standard deviation. And then what you have is you have this nice little bell curve with these kind of 7 spots labeled. You have your mean in your middle, you have 3 standard deviations to the left, and 3 standard deviations to the right. And then what you're going to go in and do is you're going to kind of label where you have these 3 numbers, the 68, the 95, and the 99.7. So the rule tells you that within one standard deviation of your mean, so meaning your mean minus a standard deviation and within your mean plus a standard deviation, so from here to here, we have 68% of observations right there, okay? So this piece right here and this piece right here come together and form the 68% of observations. Now, if we take it a little further and look to the left 2 standard deviations, look to the right 2 standard deviations, you'll notice that if we add all of these pieces together, the 13.5, the 34, the 34, the 13.5, that's going to take us to 95%. Okay, so almost all of our observations are within 2 standard deviations. And if we go 1 extra standard deviation, we pick up a little more. We pick up a little 2.35% over here, a little 2.35% over here, and we end up with 99.7% of the data within 3 standard deviations. Okay, so almost all of the data is within 3 standard deviations. Only 0.3% are in the left and the right tails. Now, if you take a look at these, 0.3% are left because if we take the entire bell curve, we have 100%, okay? We know that 99.7% are within 3 standard deviations, so we only have 0.3% kind of left over. If you take that 0.3% and you divide it by 2 to kind of split it between the left and the right-hand sides, we end up with 0.15% on the left and 0.15% on the right. Now, the other thing to kind of note here, I want you to keep in mind that this is symmetric, okay? So the 34% are there because we know that within 1 standard deviation, we have 68%. So if we take that 68% and we divide it into 2 pieces, it gives us a 34% and another 34%. So what we have here is data that represents the serum HDL cholesterol for 54 female patients of a family doctor. So what we're actually going to do is we're going to calculate our population mean and our population standard deviation using StatCrunch, and then we're going to use those values to actually label a bell curve. So what we're going to do here is I'm going to open up StatCrunch real quick. I'm going to scoot this over here, and I want to do summary stats columns. It's the only place we've gone so far, and I want my cholesterol data this time. And really all I want is, if you look back here real quick, I want my mean and my standard deviation. So I have my mean here, and I want my unadjusted standard deviation since I have a population. And if you look, I have a mean of 57.4, which is what we have right here, and a standard deviation of 11.7 when we actually round. So then what you're going to do is you're going to draw a nice little bell curve, okay, it looks something like this, and you're going to put a line right in the middle, and that's where you put your mean, okay, so your 57.4 goes smack dab in the middle. And then what we do is we take our 57.4 and we subtract a standard deviation. So we take 57.4 and we take away 11.7 and we're left with 45.7 and we write that value right there. And then we take another standard deviation away and we're left with 34. And then we take one more standard deviation away and we're left with 11.7. And then we start again at the middle at the 57.4 and we add a standard deviation and we end up with 69.1. Add another standard deviation and you're at 80.8, and add a third standard deviation and you're at 92.5. So if we look back at the questions real quick, we want to know the percentage of all patients that have a serum HDL within 3 standard deviations. So if you take a look, if we look at 3 standard deviations, we would know that 3 standard deviations goes with 99.7% of all patients. So what we could say is that 99.7% of all of our patients that have a serum HDL level within 3 standard deviations, because it's 99.7, are going to be between cholesterol readings between 22.3 and 92.5. So if we look from 22.3 to 92.5, we're going to have 99.7% of all of the patients, and that is going to be within 3 standard deviations of your mean. Now if we take a look back at question D, it wants to know the percentage of all patients that have a serum HDL between 34 and 69.1. So what we want to do is we want to look between 34 and 69.1 here. And if we take the pieces and add them together that we have here, between 34 and 69.1, we have a piece that's 13.5, 34, and another 34. And if we add those up, we end up with 81.5% of all patients that are going to have a serum HDL between 34.0 and 69.1, according to the empirical rule. Okay. We're going to move on to section 3.4, which talks about measures of position and outliers. So this is another thing that we are going to do by hand for right now, okay, and this is z-scores. Z-scores are not too difficult to calculate, and you definitely want to memorize this formula because we will be calculating z-scores so much. So really what a z-score is it represents the distance that a data value is from the mean in terms of the number of standard deviations. So for example, if you have a z-score of 0, it means that you are 0 standard deviations away from your mean. If you have a z-score of 1, it means that you're 1 standard deviation above the mean. If you have a z-score of -1, that would mean that you are 1 standard deviation below the mean. So in order to actually find a z-score, all you have to do is you have to take whatever you're interested in, which is just your data item, your x, okay, so whatever you're being asked about, and then you just subtract your mean, and then you take that and you divide by your standard deviation. Now, a z-score is unitless. It has a mean of 0 and a standard deviation of 1. So let's take a look at an example here and how we might use z-scores. So the mean height of males 20 years or older is 69.1 inches, and the standard deviation is 2.8 inches. The mean height of females 20 years or older is 63.7 inches with a standard deviation of 2.7 inches. This data is based on information obtained from a National Health and Examination Survey. So let's say that we want to know who is relatively taller, Kevin Garnett, whose height is 83 inches, or Candace Parker, whose height is 76 inches. So it wouldn't be fair to compare Kevin Garnett's height with Candace Parker's height because we know that men typically are quite a bit taller than women. So what we want to do is we want to sort of adjust for that, and we want to decide who is relatively taller. So what we do is we calculate a z-score for each of these individuals. So the z-score for Kevin Garnett is found by taking his height, which is 83, and subtracting the 69.1, which is the average for the males, and then dividing by 2.8. And we end up with a z-score of 4.96. So that means that Kevin Garnett's height is 4.96 standard deviations above the mean. Now for Candace Parker, we do the same thing. We take her height, which is 76 inches, we subtract the mean of 63.7, divide by the standard deviation of 2.7, and we get 4.56. So that means that Candace Parker's height is 4.56 standard deviations above the mean. So Kevin Garnett is relatively taller, okay, but if Candace Parker had a z-score that was higher than his, she might be relatively taller, even though he is actually taller. Okay, so this just allows us to compare kind of on an even ground. Now, we also talk a little bit about percentiles in this chapter, just because it's important to actually know how to interpret a percentile. So the kth percentile, denoted p sub k, of a set of data is just a value such that k% of the observations are less than or equal to that value. So the easiest way to talk about percentiles is just to look at an example here, okay? So let's read the top part here. So it says the GRE is a test that's required for admission to many U.S. graduate schools. The University of Pittsburgh Graduate School of Public Health requires a GRE score that's no less than the 70th percentile for admission. And so we want to actually interpret this. So in general, what it means to be in the 70th percentile is that your score is such that 70% of all individuals who took the exam scored worse, and only 30% of individuals scored better. So in order to be admitted into this program, an applicant has to score as high or higher than 70% of other people who take the GRE, or they have to also be in the top 30%, whichever way you want to think about it. So if you're talking about GRE scores, SAT scores, something like that, the higher the percentile, the better, okay? Because that means you scored better in comparison to the rest of the people who took that same exam. Okay, now we're going to talk about quartiles. Now, you guys already know how to find median, which means that you also already know how to find quartiles, okay? So what quartiles actually do is they take your data and they divide it into 4 equal parts, okay? The first quartile, denoted Q1, just divides the bottom 25% of the data, this right here, from the top 75%. So the first quartile is the same thing as the 25th percentile. Okay, now the second quartile has a name that we already know. It's actually the median, okay, and what it does is it divides the bottom half of the data from the top half of the data. So half of your data is going to be below the median, the other half is going to be above. The third quartile goes ahead and divides the bottom 75% from the top 25%. So the third quartile is the same thing as the 75th percentile. So if you want to find quartiles by hand, you can do this. It's pretty easy. We can also use StatCrunch to do it. I'll show you guys that in just a minute. But if you want to find quartiles, all you have to do is start by arranging your data in order and then finding the median, which we already know how to do. And then what you do is you just divide your data into 2 halves. You take the observations that were below the median and the observations that were above the median. And with the observations that were below the median, you find a new median of just those smaller values, and that's going to be your first quartile. And then you take the upper half of the data, so the larger half of your data, you find the median of that, and that's going to be your third quartile. So let's take a look at this example here. A group of Brigham Young University, Idaho students collected data on the speed of vehicles traveling through a construction zone on a state highway where the posted speed was 25 miles per hour. So these are the 14 randomly selected vehicles that they actually took the speed on, and we want to go ahead and find and interpret the quartiles. Now, this shows you how to do it by hand, which you're welcome to look at this point. If you want to go ahead and do that, you could pause it, take a look at that, make sure you agree, but I want to show you how to do this in StatCrunch. It's really, really easy, okay? So I'm going to go back here. I have my construction speed data already in StatCrunch. So I'm going to go to the same place that I've gone all evening, which is Stat, Summary Stats, and Columns. I'm going to select my construction speeds, which are over here. And really all I want are the first quartile, the third quartile, and then hopefully you remember that second quartile has a special name. It is the median. So I'm going to scroll back up to where the median is, and I'm going to select that as well. This time I'm going to do it correctly though, so I get all of my values together. And I'm going to click compute, and it gives me a median of 32.5, so that's my second quartile. and a first quartile of 28, and a third quartile of 38. And actually didn't even ask for the median. Oh yeah, the median was up in step 2, 32.5. So again, you can do this by hand, but I would definitely rely on StatCrunch to kind of help you with this. So if we wanted to interpret these, what we would say is that 25% of the speeds are less than or equal to the first quartile, which was 28 miles per hour, and 75% of the speeds are greater than the 28 miles per hour. Now we could also interpret the 50% below and 50% above by looking at the median or the second quartile. So we'd say that 50% of speeds are less than 32.5 miles per hour and 50% of speeds are greater than 32.5 miles per hour. Now we could do the same kind of interpretation with the third quartile. We could say that 75% of speeds are less than or equal to 38 miles per hour and 25% of speeds are greater than 38 miles per hour. Now, one other thing that we have here, and StatCrunch will calculate this for us, is our interquartile range, okay? And what this actually gives you is the range of the middle 50% of observations in a data set. So the IQR is the difference between the third and the first quartiles, and all we do is we just subtract the two in order to find it, but we can also have StatCrunch do this for us very easily by going through the same procedure but then selecting IQR. So if we take our data, our construction zone data, and I go to Stat, Summary Stats, Columns, I'm going to go here and select my construction speed, and then the only statistic I care about is IQR, so I'm going to select that and click Compute, and it gives me an IQR of 10. Now this can be done very easily. If you already have the third quartile, we calculated that a couple slides back, it was 38. And the first quartile was 28, so we just subtract the two and we get 10 miles per hour. So we would say that the range of the middle 50% of the speeds of cars traveling through the construction zones is 10 miles per hour. So we could also say that 50% of the observations are going to lie between 28 and 38 miles per hour. Okay, so let's suppose that a 15th car travels through the construction zone at 100 miles per hour. And we want to see how this value actually impacts the mean, the median, the standard deviation, and the interquartile range. So this 100 miles per hour is an outlier, okay, meaning that it's a very large observation in our data set. So we have the mean calculated, the median calculated, the standard deviation, and the IQR without the 15th car. And then what we do is we go ahead and we add in that 15th car and we recalculate these. And what you'll see is that the median does not change by very much. It only goes from 32.5 to 33. And the interquartile range also does not change very much. It goes from 10 to 11 miles per hour. But if we take a look at the mean and the standard deviation, the mean goes from 32.1 to 36.7, which is quite a large change. And the standard deviation changes by a lot. It goes from 6.2 to 18.5. So this is actually kind of demonstrating the meaning of resistance. So when we have an outlier, it affects the mean and the standard deviation quite a bit. Because if you look at the formulas for mean and standard deviation, what you're going to notice is that they include all observations in the calculations of these two statistics or parameters. So what actually happens is when you have a very high or very low observation, it kind of pulls your data in that direction. Now the median and IQR are both measures that are more resistant to outliers. So if you have a symmetric distribution, you can use the mean and the standard deviation to describe your data. But if you have a distribution that's skewed left or skewed right, the median and the interquartile range are good things to report instead. Now, I talked about outliers, that's very large or very small observations, but there is actually a way to check for outliers by using your quartiles, okay? And in order to do this, all you have to do is determine the first and the third quartiles, and then compute the IQR, and steps 1 and 2 can be done using StatCrunch. Again, you just select quartile 1, quartile 3, and the interquartile range. And then step 3, you're going to want to do by hand, and this is determining the fences. Now, fences are just cutoff points for your outliers, and in order to find your lower fence, all you have to do is take your first quartile and subtract 1.5 times your interquartile range. And then for your upper fence, you take your third quartile and instead of subtracting, you add 1.5 times your interquartile range. And then if you have a data value that's outside of those points, so lower than the lower fence or higher than the upper fence, then it would be considered an outlier. So if we take a look back at our speed data, we have quartile 1 of 28, quartile 3 of 38, and an interquartile range of 10. We already calculated these values a few slides back. Now if you want to find the fences, you take your first quartile, which was 28, and subtract 1.5 times your interquartile range, which was 10, and you get 13 miles per hour, so that's your lower fence. And then the upper fence is done the exact same way except with quartile 3 and addition instead of subtraction, and you end up with 53 miles per hour. So there aren't any values that are less than 13 or higher than 53, but if we did have any values that were less than 13 or higher than 53, then those values would be outliers. But in this case, there are no outliers. All right, last section is the 5-number summary and box plots, okay? The 5-number summary is actually really easy to find because we can do it strictly in StatCrunch, okay? And box plots are also very easy to calculate. The only thing you really need to know about the 5-number summary is what it is, okay? So if you're asked for it, you're able to actually put the 5 numbers in the appropriate order. So 5-number summary just starts with a minimum, which is very easy to find. It's just the smallest data value. And then you report the first quartile, then the median, then the third quartile, and then the maximum. And that's your 5 numbers. That's your 5-number summary. So we're going to take a look at this example here where we have Federal Reserve Board survey of credit card plans in the US. And what we have is interest rates charged by 10 credit card issuers randomly selected for July of 2005 survey. And what we want to do is we want to determine the 5-number summary, and I also want to show you guys how to draw a box plot, which is again very easy to do in StatCrunch. So we have our data here, and I've already entered this into StatCrunch. And what we want to do is we want to just go ahead and calculate the 5-number summary. So what I'm going to do, I'm just going to cover this up for a minute so we can kind of see, and I'm going to scroll down so we can see our 5-number summary. So I'm going to go to Stat, Summary Stats Columns. Again, this is kind of the only place we've gone tonight. And I'm going to select interest rates. Okay. And then if I go down here to see what statistics I want, I know that I want my minimum, so I'm going to select min. Oops, min. And then I want my quartile 1, and then I want my M, which is median. Okay, so let me scroll up to grab my median, and then I want my third quartile, and then I want my maximum. And if you notice, I'm selecting them in this order, so then when I display them, they're still in this order. So I'm just going to press compute, and what you'll see here is that I'm giving all these values here. Let me move this to the top. And we have the minimum of 6.5, the first quartile of 12, the median of 13.6, the third quartile of 14.4, and then the maximum of 14.5. So that right there gives you your 5-number summary. Now the other thing that we might want to do is to go ahead and draw a box plot, okay? So this is kind of the second major thing that we're doing in StatCrunch today. The other thing was just stats, summary stats, columns, and then you just select whatever you want. But we're also going to do box plots, which is a type of graph, okay? So all I'm going to do is I'm going to select graph and then box plot, and I want my interest rate data. And then if we go back here for just a minute, there are a couple things we want to check. We want to check the checkbox that says to draw the boxes horizontally, and then we also want to check the checkbox that tells us to use the fences to identify outliers. And you're going to press compute here, and I'm just going to widen this a little bit so we can see it a little better. And if you look here, this has drawn the box plot for us, okay? And the little dot that you see right there is an outlier. Now, if we take a look, what we can actually see is from our box plot, we can kind of see what the shape of our distribution is going to be. So if you take a look at a distribution that's skewed to the right, what you'll notice is tail is to the right on our histogram, and if you look at the box plot, it has a long tail on the right. If you look at this one, this is symmetric. It has kind of an even tail on the left and the right. So that would indicate that we have a symmetric distribution. And then if you look at this one here, we have a tail on the left. And if you notice over here, it has a very long tail on the left here. So if we take a look back at our distribution that we have here, this has a fairly long tail on the left here. So we could say that our interest rate box plot indicates that the distribution is actually skewed left. All right, guys, so that's it for chapter 3 for this week. Let me know if you have any issues working through anything, but make sure you're relying on StatCrunch to do all of these sort of tedious and difficult calculations for you.